Hmm?
Said I should take a photo.
Oh, yeah.
Everyone here okay if I take a quick photo to prove that people are coming to the seminar?
Well, I was okay last week, but this week.
This week.
This week now. Maybe wait a second. There's some. Make sure you get the speaker. Okay, well, okay. I don't know. All right.
Need to do the introduction. or-
Sounds good.
Okay. Right, we're very happy to have Meri Zaimi here today from the Perimeter Institute. She's going to tell us about Askey-Wilson algebras, Chern-Simons theory, and link invariants.
Thank you very much for having me as a speaker today. So this talk will be about some algebra called Askey-Wilson, which comes from the framework of orthogonal polynomials, and on which my work has revolved a lot around during my PhD and master studies. And I will explain its connection to two frameworks for computing link invariants. So it will be the Chern-Simons theory and a more mathematical construction due to Reshetikhin and Turaev. So I decided that for the first hour, I will basically give some review some basic concepts of both frameworks, the Chern-Simons theory and the Reshetikhin-Turaev construction. So I apologize to experts who already know a lot about these frameworks. It will be just a review of some concepts, aspects that will be relevant later. And in the second hour, I will focus on the Askey-Wilson algebra. I will introduce it, tell you why there are reasons to think that it is related to these frameworks, and then I will explain how. So in any case, the basic objects that we want to study in these frameworks are knots, which are smooth embeddings of the circle in three-dimensional space. So in order to study knots, usually we project them on a two-dimensional space. So for instance, we might have this, which is the unknot, and we can orient them. They are called oriented. So this is a trivial knot, but we might also have something less trivial, which might look like this, for instance. Hopefully I'll do this like this. So this is called the trefoil. And again, we can orient it. So by projecting knots on a two-dimensional plane, we have crossings which appear. And so we have to specify which strand goes over and which one goes below. And it's useful to define the crossing configurations like this. So this would be a positive crossing. This would be a negative one. And we can also define this configuration as L0. And then more generally, we can consider links, which are simply finite union of non-intersecting knots. So for instance, we might have something like this. Which would be a hop link. So it's a link with two components. So when we study these objects, we want to study them, of course, up to some equivalence. And we will say that they are equivalent if they are smoothly related. They're related by smooth informations. In R3, this will be called ambient isotopy. So in order to be able to say if two links are equivalent or not, we can use something very useful, which are the Riedmeister moves. So there are three of them. The first type says that so if we have some diagrams, some link diagrams, and in some part of the diagram we have a part which looks like this, we can change it by a straight strand. And similarly, if we have something like this is called the Riedmeister move of type 1. The second type says that if we have a part which looks like this, we can change it to this. And the third one, if we have some crossing like this with a strand below, we can slide the strand below the crossing. So there is a theorem, the Riedmeister, which says that two link diagrams are equivalent by ambient isotopy if and only if they are related by planar isotopies and Riedmeister moves of the three types. So if we can find a sequence of Riedmeister moves such that a diagram is goes into another link diagram, then the link diagrams, the links which are represented by these diagrams are equivalent by ambient isotopy. It turns out that sometimes it's useful to consider a different kind of isotopy, which uses only the second and third moves. This one is called regular isotopy. So in that case, we cannot use the first one, only the second and third. It will be useful when we consider framed knots and links. So now the goal is to define, I mean, the Riedmeister moves are, it's a nice theorem that we have that we can simply use these moves to get, to be able to say that two links are equivalent, but it's not very practical to know what moves to use. And so it's more practical to define an invariant. So that means to a link L, we map some quantity such that if two links are equivalent, then they have the same value for this invariant. So what we really want is to define an invariant that we can compute in some way. So it's not very useful to define the invariant which associates to each link its equivalence class. We want to be able to compute it. And that's where it's very practical to have some links invariants that come from these frameworks, such as the Chern-Simons theory and Stick-Interwave construction. And so some very useful and important link invariants that have been defined are the Jones polynomial. So this one denoted like this. It's a Laurent polynomial on the variable q to the 1/2. So to a link L, it associates a Laurent polynomial in this variable. And it was originally defined by Jones by looking at some temporally Lie algebra, so a trace on the temporally Lie algebra. This polynomial has some generalizations. So for instance, there is the home-fly PT polynomial. So this one will depend on two variables. And it's related to, it can be found as a trace on the Hecke algebra. Another one is the Kaufman polynomial. Which is also some generalization of the Jones polynomial. And this one can be found with the BMW algebra, Biermann, Murakami, Wenzel. So there is a very nice interpretation of this invariant, which was given by Witten. So it's in the three-dimensional Chern-Simons theory. Where we choose some gauge group, and depending on the gauge group, we get some invariant. In the case of the gauge group SU2, we recover Jones polynomials. SUN, we recover the home-fly PT. SON, we recover Kaufman polynomial. And the same invariants have also been recovered in a different, I mean, it's a completely mathematical construction of Reshetkin and Turaev. And this one uses quantum algebras, which are some deformation of universal enveloping algebras of some Lie algebra. So if we take here the Lie algebra SL2, we recover Jones polynomial, SLN, Jones here, SLN Hecke, and SON BMW algebra. So my goal was to try to understand. So it's quite apparent that, okay, first I should say that these algebras which appear in these frameworks, so temporally Lieb algebra, the Hecke algebra, Hecke, BMW algebra, these are all quotients of the braid group. And also they are centralizers, algebras of the quantum algebras. And so my goal was to understand how the Askey-Wilson algebra can be interpreted in these frameworks, because the Askey-Wilson algebra is related to these kind of quotients of the braid group, and more specifically to centralizers of quantum algebras, and related to the special case of UQSL2. And so this was the main goal. And so now I will explain some basic aspects of both both constructions for computing Lie invariants, so Chern-Simons theory and Reshetkin-Turaev invariants. And later, in the second part, I will explain how this Askey-Wilson algebra relates to both constructions. So I'll start by reviewing some aspects of Chern-Simons theory. So we will take a three-dimensional manifold, which is the space-time. We'll take a Lie algebra. Associated, okay, so the Lie algebra will have generators. Let's denote them TA. And it's associated to some Lie group G, which is compact, simple. And so we have the gauge field, which is a one form, and can be written in terms of the generators. And the Chern-Simons action can be written as so kappa is a coupling, and we have a integral over the three-dimensional manifold of the trace of A wedge A plus another term. So in this talk, I will really only take M to be R3, or we can also take S3, but R3 will allow me to keep the deformation parameter generic, so I will stick to R3. So in Chern-Simons theory, we want to compute, we have some observables, the Wilson loops. So I forgot to say, so this action is topological. It does not depend on a metric. And we expect it to lead to a theory with observables. We also want observables which are topologically invariant. And so their expectation values, we expect them to lead to topological invariance. So the Wilson loops is defined like this. It's a trace. Here we have the path ordering operator. And rho is a representation of the Lie algebra. So we take the trace in this representation. And so here K will be an oriented knot in the manifold, which will be R3. And we will also see that it is colored by the representation rho. And then we can consider a product of Wilson loops with several components, Ki, associated to representations rho I. And so this L means the link formed of these components colored by the representation rho I. So what we want to compute are the expectation values. Defined like this in terms of the path integral, in the path integral formalism. So in the abelian case, it's quite, well, I mean, it's possible to use the path integral formalism to directly compute the expectation values. And the answer looks something like this. So it's an exponential Here, Ni and Nj are charges associated to the representations of U1. And here we have the linking number which appears. So chi of Ki and Kj is the linking number of Ki and Kj. So it means the number of times that the knot Ki winds around the knot Kj. So for instance, in the case of the hop link, that linking number would be just 1. And it's clearly an invariant of links. You can try to use the red master moves and you'll see that it will never change the linking number. And there's also a nice way to write this linking number in terms of the Gauss integral, which uses a metric, but at the end, the result does not depend on the metric that we use, in the same way that when we draw links on planar diagrams, we project, but at the end, the number will not depend on the projection that we use. So the reason I'm talking about the abelian case is just to remark that here we have cases where we have to consider the self-linking number, which is a little bit ambiguous to define if we only consider knots and links. And so in order to define the self-linking number, we have to introduce a framing on the knots and links. So a framing will be a continuous and nowhere vanishing vector field, which is normal to the knot K. And for any component K, we add this kind of framing. So for instance, if we have this kind of trivial knot, we might simply do a framing which is also trivial, but we might also choose to pass it here and then below. And in this case, the self-linking number would be non-zero. And so there is this framing which has to be considered in Chern-Simons, in the quantum Chern-Simons theory. So a way to deal with the framing, instead of always drawing the framing around the components, we can simply continue to use link diagrams, but with the convention of a vertical framing. So that means that the framing will always be perpendicular to the projection plane. And so when we do this, we can see that this kind of diagram, if we view it with a framing, it can be viewed as a ribbon, in fact. And if you try to straighten it, you will have some twist in the ribbon. And so this will not be anymore equivalent to this. And similarly for the other one. It's not anymore equivalent to the straight strand when we are considering framed knots and links. And that's the reason why regular isotopy is relevant to consider in this context. And so in the following, I will use this convention and define the invariant associated to Chern-Simons as the expectation value of the Wilson loops with the vertical framing convention. So it's an invariant of regular isotopy for link diagrams, which are oriented and colored. But it can also be viewed as an invariant of ambient isotopy for framed links, which are oriented and colored. Yeah, and just wanted to mention also that a way to talk about the framing is to introduce the Reith number. The Reith of a link is the number of positive crossings minus the number of negative crossings. where by positive and negative, I mean the diagrams that I draw in the beginning, L plus and L minus. And so this kind of component would have a right of +1, and this one would be a right of -1. And so when the framing changes, the right number of a component changes. So although we are considering regular isotopy, it's not difficult from a regular isotopy invariant to get an ambient isotopic invariant if we have the property that when we apply a right master move of type 1, it's not equivalent to the straight strand, but it can be viewed as this with a coefficient A. And this one will be the inverse of this coefficient and the straight strand, because in that case, we can simply define, so take this for our invariant. And then with this, we get an invariant of ambient isotopy, because this coefficient here will take into account the fact that this does not, it will compensate this coefficient which appears here when we apply the right master move of type 1. So, okay, here I considered only one type. I mean, each of the components are associated to some representation. So if we have different representations, of course, we would have to multiply by different coefficients for all the representations that appear. So in Chern-Simons theory, we can, the expectation values will be expressed in terms of this deformation parameter. So I'll use this definition here. It's Q, which will be the exponential of minus I pi over kappa. So as I said, some situations, kappa has to be an integer in order for the theory to be cage invariant. And in those situations, Q has to be a root of unity. But if I understand the theory correctly, on R3, Q can be kept generic. And so I don't have this problem of roots of unity. That's why I will stay on R3. So some facts about the non-abelian Chern-Simons theory. They're in the canonical approach to find the solutions. We can compute a monodromy matrix, which has the following form. So this monodromy matrix represents the effect of doing this kind of braiding of two punctures, exchanging two punctures. I mean, doing a loop with one puncture around the other. And so the monodromy matrix will have this form. And here, this is summed over A. And this element here can be written in terms of Casimir elements for the representations. I mean, okay, it depends on how we normalize the generators, but with some normalization, for instance, we can simply write it as, okay. I think it will be a factor of 4. Depends on the normalization, but it will be proportional to this kind of Casimir of the representation. Okay, I will define this in a moment. So this is the Casimir associated to representation row 1, row 2, and row 1, 2. I mean by that, okay. if we take the tensor product of row 1 and row 2, we get some rather direct sum of some other representations that I will denote row 1, 2, t, which are irreducible. And so for each of these irreducible representations, we get some value here associated to that representation, which appears here. And by knowing this the form of the monodromy matrix, we know, because of this, the eigenvalues, and it's really useful for determining relations among linked diagrams. So the strategy for the non-abelian theory will be basically to find relations among diagrams and be able to use some these kind of relations in order to completely determine the invariant associated. So something else that we know is what happens when we change the framing. So let's say we have a component in the representation row like this. It is the same as adding this factor here with the Casimir element associated to the representation row and having the straight strand. And similarly, if we have this, we can replace it by the straight strand up to this coefficient here. Some other very useful properties is the fusion of Wilson loops. So let's say we have two Wilson loops like this with associated to some representation row 1 and row 2. This can be fused together and we get a sum. I mean, we get the loop associated to the representation row 1 tensor row 2, and it can be expressed as a sum over the irreducible components. So So using these kind of properties in the Chern-Simons theory, Witten has shown that the solution for SUN, for instance, is related to the Home-Fly-Petit polynomial. So a way to describe this, so if G is SUN, and all the representations are the defining one or standard representation, then the invariant is uniquely defined by the following properties. So it is defined by regular isotopy. We have the normalization of the unknot, which will be like this. This is sometimes denoted as the Q number, NQ number. We have the change of framing, which will be given by this. So this factor n square minus 1 over n, it's related to the Casimir element of the representation. It's inverse. And we have some gain relation, which says that whenever we have some diagrams which are related like this, so they are the same everywhere except in some region where they differ like this. So in some of them, one of these have the positive crossing, the other one has a negative crossing. They are related to the diagram with L0 crossing. So this is the scaling relation for SUN. it's related to the fact that if we take two standard representation of SUN, these are the Young, this is the Bratelli diagram. So we get either the symmetric one in the decomposition or the anti-symmetric one, basically two eigenvalues for the monodromy matrix, and we get this kind of scaling relation. So as I said, this is a regular isotopic invariant. We can renormalize it in order to get an ambient one. In that case, the scaling relation will change like this. If we renormalize it using these coefficients here, we will get a new scaling relation, which looks like this instead. And this would be, and we can use, in that case, ambient isotopy. And so it's completely related to the Homsai-Petit polynomial, which has variable t, which is equal to q to the n, and variable z, which is equal to q minus q inverse. So I'll just write. Yeah, so basically, okay, I'll define the Homsai-Petit polynomial. So this polynomial is defined uniquely by ambient isotopy. We normalize the R naught to 1. And we have this a scaling relation with two variables like this. Minus. This defines uniquely the Homsai-Petit polynomial, and so by comparing with Chern-Simons theory, we get that this invariant for Chern-Simons up to some renormalization for with the coefficient related to the sec with the third property above. It will correspond to the Homsai-Petit polynomial with variable qn here and q minus q inverse. The Jones polynomial is a special case of the Homsai-Petit polynomial, where we take, so Jones polynomial, it corresponds to taking the Homsai-Petit polynomial with q here and q1/2 minus q minus 1/2 here. In this case, will appear when we take SU2. So there is a more practical way to compute the Jones polynomial, which is using the Kaufman bracket. So the Kaufman bracket is an invariant of regular isotopy. And it's defined on unoriented link diagrams. So the R naught here will be normalized to this, and we denote it X. Again, we have this kind of type 1 move. And here we have a much, it's a simpler scale relation, which looks like this. So if we have this kind of crossing, we can replace it by two straight strands, or it's a linear combination with another kind of like this kind of caps and cups. And so it says that whenever we have a crossing, we can eliminate it by this kind of diagrams here. So it's very useful to compute an invariant with this kind of scale relation. And the connection with the Jones polynomial, there's a very straightforward connection. So the bracket polynomial is equal to, so here we have to normalize. We have this for the Jones polynomial, and we have to add this coefficient here to take into account the fact that one is a regular isotopy and the other is not, is ambient. And so we have this nice connection between the Kaufman bracket and the Jones polynomial. And so it turns out that if we consider gauge group SU2 in Chern-Simons theory and all representation in spin 1/2, we can write the invariant in terms of these bracket polynomials with an exponential factor here, which takes into account the right of the diagram. And here we have the bracket polynomial. So it's very useful when we have SU2 and spin 1/2, we can compute the invariant with this relation. So this is the most important result that will be useful for me because, as I said, the Askey-Wilson algebra will be related to SU2 and UQSL2, and it will be a key point in interpreting the Askey-Wilson algebra later. So these are the aspects of Chern-Simons theory that I wanted to discuss, and now I will try to explain more the connection with the algebras. And this will lead us to the Reshetikhin-Toraev invariant. So the idea is to consider the braid group. It will play a major role in the algebraic interpretation of the invariants. So the braid group on n strands is generated by some invertible elements that I will denote sigma I. I goes from 1 to n-1. And the relations are the following. So if I and j are far enough, the generators commute. And by far enough, I mean that I minus j, the absolute value is bigger than 1. And we have the braid relation. For other values of I mean for I from 1 to n-2. And with this definition, we also have a natural inclusion of the braid group on n strands into the braid group on n+1 strands. And so this is Artin's presentation of braid group, and it has been shown that this algebra is, this is the group, it's equivalent to the group of braid diagrams where the generators sigma I are mapped to a diagram of on n strands where on the ith and ith+1 strands we have this crossing, overcrossing. And for the inverse, we have the undercrossing. And we can take a product of these diagrams by concatenating the diagrams vertically. So my convention will be that, so if I write, for instance, sigma I inverse sigma I, I'll start with the braid sigma I. So I'll just write this part here of the braid. It will be an overcrossing like this. And then I stack on top of it the inverse, which is the undercrossing like this. And we consider braids, these diagrams up to some isotopy of braids. And so here we can see that we can deform the braid and put this strand on the left. So it should be equal to this, which is the identity. Similarly, if I have started with the inverse here and sigma I here, and we can also look at what happens, I'll try it here. If we take, for instance, sigma 1, sigma 2, sigma 1, so this corresponds to taking this. So I start with sigma 1 here. Here I do nothing, then sigma 2, then again sigma 1. And this diagram should be equivalent to taking sigma 2, sigma 1, sigma 2, which here we start with sigma 2, then sigma 1, and then sigma 2. And we see that basically this equivalence of diagrams is similar to the right master move of type 3, while this is similar to the right master move of type 2. And so it is apparent that braid groups are quite useful for studying links. And I will make this more precise with the following statement. So we can clearly see that if we have a braid, so let's take this kind of braid here. And let's say we take its closure, which means that we connect the endpoints together. Then this closure gives a link diagram. But there is a stronger statement. It's Alexander's theorem, which says that any link can be obtained in this way. However, sometimes we can have two different braids and their closures might lead to the same link. And so for this reason, it's not always obvious to work with braids. But we also have something, we have Markov's theorem, which explains which braids lead to equivalent links. So Markov's theorem says that two braids give the same closure up to isotopy if and only if they are equivalent under the two Markov moves. So the Markov moves are as follows. This first one says that a braid alpha and a conjugation of it are equivalent. It will give the same closure. So here alpha and beta both are in the braid group on n strands. And the second Markov move says that if alpha is a braid in Bn, which is included naturally in Bn plus 1, then we should consider that alpha is equivalent to taking alpha and adding here the last generator on the braid group on n plus 1 strands, or its inverse. So clearly here the conjugation is related to the fact that we are taking this closure, and so there is some cyclicity. If we take a braid here and its inverse here, we can simply put this one on top of the other and it will go to the identity. While the Markov move of type 2 is rather related to what happens, it's similar to the Redmaster move of type 1, because let's say we have some braid alpha on certain number of strands, and here before having alpha we add this generator on the last 2 strands, so it will, for instance, we have this crossing here, and here we still have our strands, and then when we take the closure like this, well, we see that this kind of loop appears, which is related to the Redmaster move of type 1. So now we see that using Alexander's theorem and Markov's theorem, we are close to be able to obtain a link invariant using braids, the braid representations of links. And the idea will be to define something called a Markov trace. So we want to define a linear map which will take a link to something that we will compute using the braid representation of the link. And we want this to be a link invariant. So as I said, this is related to the concept of a Markov trace because of the 2 conditions of Markov's theorem, we want something that, so we often denote it like this. So if we take this map for 2 braids in the braid group on n strands, we want to be able to commute them because of the cyclicity and this conjugation property here. And we also want something like, so if we take a trace on the braid group on n plus 1 strands with some element x of the braid group and sigma n, we would like to get the trace on the braid group n of the element x of Bn. So this is the idea of the Markov trace. So these Markov traces, we want obviously to apply them to elements which satisfy the braid group relations, but the braid group is really large. It's infinite if we take only the braid relations. And so something very useful when we study the braid group is to study its quotients. So a very useful quotient is the Hecker algebra. So in case of the Hecker algebra, we still have the braid generators with the braid relations, but we add a quadratic relation, which looks like this. And if we expand this relation, it will give, it can also be written like this. So sigma I minus sigma I inverse is equal to Q minus Q inverse. And so as we saw, sigma I is associated to the braid, to the overcrossing. Sigma I inverse is the overcrossing. And this quadratic relation says that these 2 braids should be equal to a coefficient times the identity. So it's completely similar to the scaling relation that we had previously in the Homfly-Petit polynomial. And that's why when we take a trace over this kind of Hecker algebra with some properties which satisfy the Markov trace. So here we can renormalize the braid elements, let's say t and t minus 1, and we basically get the scaling relation of the Homfly-PT polynomial. Another quotient which is very interesting is the temporally linear algebra. So in this case, we are in Hecker algebra and we add an additional relation, which is sometimes called the Q anti-symmetrizer. So we take this kind of element. And we put this to 0. The temporally linear algebra has another very nice presentation. If I and j are far enough, we have that they are quasi-idempotents, or we can normalize them in order for them to be idempotents. And we have these last relations here. And this temporally algebra has also a very nice diagrammatic interpretation where the generators EI are mapped to diagrams with some strands from 1 to here I plus 1, n. And here we have this kind of hook diagram, continues like this. And when we take a product of two of this, the same generator, we get something like this. We get a loop. And because of the relations of the algebra, this is proportional to the diagram where we have this. So we can remove the loop up to a coefficient 2q number, while the last relation looks like in terms of diagram. So we take, for instance, EI here, then we take EI plus 1, and then again EI. And by isotopy of the diagram, this can simply be put into a straight strand. And so we recover indeed EI. And similarly with the other one, where we take EI and EI minus 1. And so, in fact, the Markov trace, it will be possible to define this kind of invariant more generally on central algebras, which are centralizers of quantum groups, and it will be a very explicit construction because it will be based on representations of the quantum groups. So at the end, it will consist of taking a trace on a matrix. And so, because here we can define the Markov trace in a very abstract way and compute it recursively, but in the quantum group construction, at the end, we will be able to compute with matrices. And as I said, the Hecker algebra and temporally linear algebra are centralizer of quantum algebras. And so they can be viewed as a more a special case of this Reshtikin-Turev construction. So in order to understand this construction, let me talk a bit about the quantum algebras. So the idea is that if we start with a Lie algebra, complex Lie algebra, which is semi-simple, we have its universal enveloping algebra, where we can take products of elements in G, and the only relations are given by the commutation relations. But this one is associative. And then we can deform it into something which is UQ of G. So we deform it with a parameter q such that when q goes to 1, we recover the universal enveloping algebra of G. And these kind of algebras have a quasi-triangular Hopf algebra structure. In fact, they even will be ribbon Hopf algebras. So this means a lot of things, but among the things that it means and which will be useful for me later, there is the fact that we have a co-multiplication which is a algebra homomorphism into the twofold tensor product. And it respects the co-associativity property. We have other things like a co-unit, an antipode. I won't discuss them very much, but the thing I will discuss is the universal R matrix. Which is an invertible element in the twofold tensor product. Such that we have the following property. So if we take the opposite coproduct where we exchange the factors of the tensor product of any element of the algebra, it's the same as taking this conjugation by the R matrix of the usual coproduct. And we also have the quasi-triangular conditions. It can be written like this. So the coproduct allows us to define representations on tensor products of representations of UQ of G. And the R matrix tells us what happens when we want to exchange the two factors. So it gives an isomorphism between the representation, let's say, VW and WV, where the vector spaces are swapped. So if the R matrix is trivial, we say that the algebra is co-commutative, which is the case for the universal enveloping algebras of Lie algebras, but for quantum groups, quantum algebras, this R matrix will be not trivial, and we will have non-co-commutative algebras. And I think this is one of the reasons that quantum groups were introduced, because this R matrix with these properties satisfies the quantum Yang-Baxter equation. And so if we have some representation of the quantum algebra, and if we define this braided R matrix, so I think this most makes sense when we apply it on a representation. This means that we are swapping the factors of the tensor product associated to the spaces I and I plus 1. And we can act on a product of representations. if we define this braided R matrix, then we get that exactly that this satisfies the braid relations. So let me denote shortly Ri for I plus 1. We get this kind of braid relations from the R matrices. Moreover, the braided R matrix commutes with the coproduct. And so that means that it will be in the centralizer of the quantum algebra. And also, well, in several cases, we will also have some elements which can be constructed quite generally. Let me call it for now mu, and I won't really explain how it can be found. It's an element of the algebra. So in this case, if such an element, this kind of elements can be found in Hopf algebras, which are also ribbon quasi-triangular Hopf algebras. And the property that we will need for this element is that it commutes with the R matrix when we take this tensor product. And also if we take some partial trace with this element here, partial trace on the first space in some representation, we will get some coefficient here, or its inverse, and the identity. So basically, we are able to define a Markov trace using the braid representations given by the R matrix on these quantum groups. And depending on the quantum algebras that we are considering and the representations, the R matrix will have some characteristic equation because it will have some eigenvalues. And so it will lead to the same scale relations as I was talking about the Heckel algebra or temporally algebra. And in fact, the construction of Reshtiki and Tuareg is much more general. It can be understood in terms of ribbon categories. And in their construction, they have some ribbon graphs, which can be viewed as some framed tangle diagrams, which are colored by representations of the quantum groups. And each diagram is mapped by a functor to a morphism of UQ of modules of the quantum algebra, and so it will, if it is an endomorphism, it will belong to the centralizer. And so a tangle diagram will correspond to an element of the, a morphism of UQG modules. It's a very general framework constructed by Rishtikin and Tuareg. So basically in their diagrams, if you have these crossings, it will correspond to the R matrix. And if you take the undercrossing, it will correspond to the inverse. And in their diagrams, you also have some cups and caps like this, which will be oriented. So depends on the conventions, but usually, okay, in my conventions at least, when an arrow goes up, it will be associated to a vector space, and when it goes down to a dual vector space. And so this kind of parts of a diagram will correspond to co-evaluation maps and evaluation maps. And so from a diagram, we can write a morphism. And if the diagram is completely closed, it will give the trace, the quantum trace of the, so let's say it's a braid. So we have a link, we can represent it by a braid. And in this construction, we can take its quantum trace, which basically comes to taking a trace of the action of this braid on the vector spaces with which we have colored the strands in the diagram. And here we take this element mu n times. And this will give an invariant of regular isotopy. And we can renormalize it in order to get an ambient isotopy. So this is the idea of the Reshetikhin-Turaev construction. And if we take the quantum algebras SLN, we will get the R matrix associated to SLN, which will be a representation of the Hecker algebra. If we take SL2, it will be a representation of the Temple-Lilib algebra. And with these traces, we will get the same invariance as before. So this was the story of these two constructions for link invariants. And now I just wanted to explain how the Askey-Wilson algebra can be understood. I don't know how much time I have left to.
We have until 4. Normally it's some point in the middle. We take a break because there's actually coffee in the lounge. So maybe
Okay.
we can stop until
Yeah.
25 and come
Yeah,
back.
yeah.
That's more likely to resonate with people.
This might be everyone now. I'm not sure. I think whenever you're ready.
We should unpause.
I think, yeah.
Oh, you did?
Pause.
Great.
You can shut it.
Okay, so now I will explain, I will give more motivation on the Askey-Wilson algebra and how we can understand it in these two frameworks. So the Askey-Wilson algebra comes from the frameworks of polynomials, orthogonal polynomials. I will call them polynomials of Askey-Wilson type. So we have some families of polynomials with some variable x of degree n. It could go to infinity. It could also be a finite family. And this satisfies some orthogonality relation. It could be a continuous one, like something like this. Where this is the weight and this is the normalization. It could also be discrete orthogonality relations, which we can write like this. So x will take some values in some set. And here, some discrete set. Again, we have this kind of orthogonality. So these polynomials of Askey-Wilson type are can be expressed in terms of Q hypergeometric series. Hypergeometric series, which are of this general form. So with some parameters A1 up to AR and B1 up to BS, with Q, C here. So it's a series, an infinite series with some Pocamer symbols here. Which are deformations of the shifted factorial. There is a minus sign. And here, z, powers of z. This. So this, okay, these kind of polynomials are organized in the QSK scheme. And in this scheme, the most general ones are the Askey-Wilson polynomials, which are of type 4, 5, 3. And these polynomials have some things in common. And it is that they satisfy a 3-term recurrence relation. And in fact, any family of orthogonal polynomials satisfies such a recurrence relation, but the converse is also true, actually. Any family of polynomials which satisfy a 3-term recurrence relation will lead to an orthogonality relation for this family. But okay, so the recurrence relation can be written like this. So here we will take as variable mu of x for the polynomials. And so if we multiply the polynomials by the variable, we get a 3-term recurrence relation with some coefficients, let's say an, n plus 1, bn, pn, and cn, pn minus 1. So here the degrees are shifted, but they also satisfy a second order. Could be a Q difference or differential, depends on the situation. Equation. So here I will write a more different case, which looks like this. So in this case, we multiply by something which depends on the degree of the polynomial, and we get a linear combination of elements where the coefficients depend on x, and the x variable is shifted. So here we will have x plus 1. We can have just mu x and the n mu x minus 1. These two equations can be viewed as eigenvalue equations. And in fact, it will define a bispectral problem. So let's say that we define p, the function of two variables n and x, as the polynomial with variable degree n evaluated at x. Then these two equations, we can view them as if we have some operator L, which acts on the variable x, such that when we act on the polynomial p and evaluate it at n of x, we get the eigenvalue lambda n. And another operator which acts on the variable which is the degree n. And when we evaluate it, we get an eigenvalue which depends on x with the same polynomial here. So these polynomials are solution of a bispectral problem of this form. More concretely, what we do, we view these operators in some realization. So let's say we want to view them as operators acting on the variable x. Then I will define L as the operator which acts on functions of x in the following way. So we'll take these coefficients and shift the variable. While the operator M will simply multiply by mu of x. And so on the basis given by the family of polynomials Pn for different degrees, could be infinite or let's take it finite here. It's clear that if we act with L on this basis, we apply this formula and we get that L on Pn will simply be lambda n times Pn, while M, which is multiplication by mu of x, if we act on this basis using the recurrence relation, we see that it will be a linear combination of elements with degree +1, n, and n minus 1. And so this one will be a diagonal, will be diagonal in this basis, while this one will be tri-diagonal. And these two operators, we can compute their relations. They will generate an algebra. In order for the algebra to close, we also need to consider their Q commutator, which is defined as Q Lm minus Q inverse ML. And by considering these elements and the algebras they form, that is how we arrive at algebras of Askey-Wilson type. So every family of the Q-ASCII scheme will lead to such an algebra. The most general one will be the Askey-Wilson algebra. And in some irreducible representations of this algebra, there will be a basis where one of the operators will be diagonal, the other one will be irreducible tridiagonal, and vice versa. There is a basis where this one will be diagonal and this one will be irreducible tridiagonal. This kind of matrices are said to form a Leonard pair. And so the theory of the Askey-Wilson representation theory of Askey-Wilson algebra is closely connected to Leonard pairs and tridiagonal matrices. So the Askey-Wilson algebra has some nice connections to physics. It's related to integrable systems. It's related to the ASEP models, where we have particles which can hop on a chain with certain probabilities. It's related to the Bethe-Ansatz, Q-Onsager algebra, and many other things. But the connection that I want to explain today is with the quantum groups, more specifically with UQ-SL2. So UQ-SL2 has the same representations. I mean, they are in correspondence with the representations of SL2. So they are labeled by some spins, half integers or integers. And so if we take, let's say, 3 spins, we can couple them in different ways. So we can start with the 2 first and then the third one. Or we can start with the 2 last spins. And these 2 ways of recoupling the scheme, the spins, should be related by a transformations little basis. This is called the Raka problem, to find how they are related by a change of basis. So if we take simply the Lie algebra SL2, the Raka problem will be related to the Raka polynomials, because the coefficients which allow to pass from one basis to the other are given in terms of Raka polynomials, while for UQ-SL2, we will have pure Raka polynomials, which are a finite version of the Askey-Wilson polynomials. So they are also called 6J symbols. And this connection with UQ-SL2 and these polynomials is understood algebraically in terms of the centralizer. So the Askey-Wilson algebra is realized as the diagonal centralizer of UQ-SL2 into its threefold tensor product. And because of this connection with centralizers, we also have some nice connection with Schur-Weyl duality, for instance. I just wanted to mention it. So the usual Schur-Weyl duality puts in connection, for instance, we can take SLN. We can act with SLN on a tensor product of vector spaces, which would be the here. Okay, let's take complex vector space of dimension n, and we can take an n-fold tensor product. And on the same space, we can act with the symmetric group algebra. And these two algebras are full mutual centralizers of each other. This is the Schroval duality. And there's a quantum version of it for UQSLN, which works the same, but in this case, we have here the Hecker algebra, which is the Q-deformation of the symmetric algebra. And so if we take the special case of UQSL2, here we will get, in fact, a quotient, which will be the temporally Lieb algebra. But if we want to consider a more general setting where we can change what are the representations here, so for SL2, we have many other representations of other dimensions than 2. So let's say we take C2J1 plus 1 of dimension 2J1 plus 1, and we take one of another dimension 2J2 plus 1, and let's take a third one. Because of this connection between the Askey-Wilson algebra and the kind of universal centralizer, we can, whenever we choose some representation, here the centralizer will be a quotient of the Askey-Wilson algebra. So the Askey-Wilson algebra will surject on the centralizer of UQSL2 in this space. And in case where we take the same vector space, but it could be of higher dimension than 2, then it's also a quotient of the braid group algebra. And so in this situation, we get an algebra which is both a quotient of the Askey-Wilson algebra and the braid group. And so clearly they're related. So in some past work, we have related those very precisely and obtained an algebra which can be expressed explicitly in terms as a quotient of both the Askey-Wilson algebra and the braid group. And because of all these connections, I think you can see that many of the algebras that I have already mentioned appeared, the Hecker, temporally Lieb, braid groups in general. It's expected that the Askey-Wilson algebra also can be interpreted in the frameworks where we compute invariants. So let me describe this algebra more precisely. It's generated by some elements C12, C23, C13, which don't commute in general, and some central elements C1, C2, C3, C1 to 3. And they satisfy the following relations. There are two other relations which have the same form, but instead we kind of take a cyclic permutation. So 2, 3 here, 1, 3 here, 1, 2 here. Sorry, this is 3 and this is 2. So here it will be 1, 2, 3. Or we can take 1, 3, 1, 2, 2, 3, 2, 3, and 1. And here Q is not it's a complex number and it's not root of unity. There's a Casimir element. So it's an element which will commute with everything, and it will be written in terms of the generators C12, C23, C13, and the other ones. It's of order 3 in these generators. I'll try to write it a little bit long. So it's not a very simple element, but it's useful to define it. And the reason I am defining this element is because there is a quotient of the Askey-Wilson algebra where we impose the relation that this Casimir element, so here it's a definition, but here we impose the relation that it's equal to an element which can be written in terms of the central element of the algebra. And the reason for introducing this quotient is that in the realization of the Askey-Wilson algebra as a centralizer of UQSL2, this kind of relation will be satisfied. And since I will consider such a realization, I will use the quotient, this quotient, which is called special Askey-Wilson algebra with a 3. And so now what I'll explain is that these generators, we can understand them in terms of some tangle diagrams that I will define. So these tangle diagrams will be colored by representations of UQSL2. And I will use the color blue for the representation of spin 1/2, which is the defining representation. Otherwise, I will just not specify the representation. So these tangles will look like 3 strands with some of them which are enclosed by loops. And the strands which are enclosed correspond to the indices here. So again, I will consider these kind of diagrams of up to regular isotopy, and we can take products of them by stacking them vertically, and we can also add braids. We can take products with braids. And so it's clear with these diagrams, if we use regular isotopy, it's clear that these 3 first diagrams here will commute with all the other ones because the loops can simply be slipped down or up the others. And this one will also commute with all the others because this loop encloses we can always slide it up or down around the other loops. But the other 3 elements here, generally, they don't commute with each other. And so my point will be to argue that if we consider these kind of diagrams with the product, they will satisfy the relations of the Askey-Wilson algebra. And I will argue this in both the Chern-Simons theory and Reshtikin-Trev construction. So we really have all the tools necessary to see why this is the case. So in case of Chern-Simons theory, the key point is the connection with the bracket polynomial. Because if we view these diagrams from the top, they look like punctures and encircled by some loops. So for instance, we might have something like this. And it has been known that the Askey-Wilson algebra can be interpreted using some Kaufman-Skene bracket and on punctured surfaces. But here what is nice, I think, is that we kind of have this rule which comes directly from the representation of UQSL2 in the framework that we are working. And so what we want to do is, for instance, consider this kind of loop, which which is associated to the product A12 with A23. And we want to compare it, for instance, to the other way, where we take instead A23 and A12. So in this case, this one will be on top. So the idea will be to use what we know about Chern-Simons theory. So we know that when all the spins are 1/2, we can use the bracket polynomial to compute it. And here, in order, I mean, maybe there is a method which is faster and doesn't require the spins to be put into 1/2, but this is the method that I have used. So the spins that we have here, J1. Okay, so first, just mention that the fusion property can be used in order to reduce the spins that appear, because if we take spin J minus 1/2 and 1/2 here, using the fusion, we can write it as the loop associated to the product of J minus 1/2 with 1/2, which when it decomposes using the decomposition rule of SL2, we get one spin of J, one loop of spin J, and another one of spin J minus 1. And so using this relation, any loop of spin J can be put into a loop of spin J minus 1/2, 1/2, or J minus 1. So we can reduce recursively the spin like that. The loops with spin 0 will not contribute to the expectation value. And so we can always take our set of spins J1, J2, J3, and use this fusion rule to put this into several punctures, but with spin 1/2. I will denote it like this. So we have some sets of spins 1/2. So after doing this procedure, we can simply remove the orientations of our loops and diagrams and compute the bracket polynomial. So, and so now we will have this kind of diagrams. I will not write the punctures, but you can imagine that we have these 3 punctures here. So this would correspond to the diagram A12, A23. And let's add this cube coefficient here. Here we get this diagram. And here, the other diagram, which goes around the second set of punctures. So if we use the Kaufman bracket, the skein relation of the bracket Kaufman bracket polynomial, which looks something like this. So using this skein relation, we can simply eliminate all the crossings in our diagrams. And so if we use this recursively on the crossings which appear, we get a relation with some other diagrams where we encircle here the first set of punctures and the third one, or we can encircle all of them and the middle one. So this corresponds to other diagrams of the Askey-Wilson algebra. So this would be C1, C3, C2, C1 to 3. This is C1, 3. And these are C1, 2 with C2, 3. And so all that remains now is to use the connection with the Chern-Simons invariant. So it was almost the same as the bracket polynomial, but with some exponential factor. And what we see here when we compare these diagrams, so we can add again orientations in order to get some right numbers. But what we can see is that if we compare these diagrams together, the only difference for the right number will be in the second set of punctures. So either they are encircled by two loops or by nothing. Each time a puncture is encircled by a loop, so in the two-dimensional, well, if we look back at the tangles, it looks something like we have a loop like this, and let's say a strand like this here.